Let's now talk about Tor, a network and piece of software that many people use both for anonymous and private communication, as well as censorship circumvention. Tor actually has roots in a protocol called a MIX. This was an early proposal for anonymous email communication by David Chaum. The idea was to use the combination of public key cryptography and a trusted email remailer to anonymize the sender and receiver of various emails. The idea is that the MIX server would receive a bunch of emails and then inject random delays to the recipients, thereby making it very difficult for a passive observer in the middle of the network to correlate the sender and the receiver of a particular message without knowing explicitly the to and from addresses in that mail. Most modern anonymity systems use the concept or idea of a MIX as the basic building block. Let's take a look at a basic MIX design in more detail. Here we have some senders on the left who may be wanting to send messages to some receivers on the right. A sender could encrypt a message with the public key for recipient B and subsequently encrypt that with the public key of the MIX. The MIX could then remove that outer layer of encryption, before ultimately sending that message to B. This kind of looks like layers of an onion and is the fundamental building block as well of onion routing systems like Tor. The idea is that an observer observing that initial message wouldn't necessarily know that the message A sent was destined for B, and someone seeing the second part of the exchange coming out of the MIX wouldn't necessarily know that the message being sent to B was coming from A. Now, of course, if this system had only one message, as shown in this diagram, it would be relatively easy to correlate the input message and the output message. But by adding more messages and inserting random delays at the MIX, it becomes more difficult for an adversary to correlate the messages that are being sent on the left side of this picture from those that are being received on the right side. One of the issues with a MIXNet, of course, is that its anonymity properties depend on delaying the messages at the MIX. And so for applications that depend on low latency, including web browsing, but also things like video conferencing, gaming, and so forth, a basic MIX design doesn't work as well as it might for applications that are more tolerant of delay, like email. It's also possible to build a so-called cascade of mixes or a network of mixes, sometimes called a MIXNet. In such a scenario, an attacker might control or be able to observe the messages going into or coming out of any single MIX. But in order to correlate messages between sender and receiver, an attacker would need to control more than one MIX, or potentially all the mixes on the path, or at least the MIX at the entry point from the sender and the exit point from the receiver. This is the basic idea of Tor's threat model. The idea is that an adversary might be able to observe certain parts of the Tor network, but it's unlikely or uncommon that an adversary would be able to compromise all of the mixes or nodes or relays or vantage points along a path from a sender to receiver, or even the entry point and the exit point to a MIX cascade or a network of mixes. And by making it difficult to compromise those 2 points, it becomes more difficult to correlate the traffic between a sender and receiver and thereby link communication between those 2 parties. Of course, certain attackers might be able to gain control of this network at both the entry and the exit point and perform what's called a traffic analysis attack. And there are various defenses against those kinds of attacks as well, such as injecting padding or random timing delays. As discussed, MIXNets have some disadvantages. Public key encryption and decryption at each hop along the way are computationally expensive, and as we've discussed, basic MIXNets have high latency. That's okay for some applications like email, but it's not ideal for applications that depend on low latency, like web browsing. So there's some desire to have a low latency anonymity network or MIXNet, and that's the basic motivation for Tor. The idea behind Tor's design is to use public key cryptography to establish a circuit that uses pairwise symmetric keys between hops along that path, thereby avoiding the need to perform expensive public key operations at each hop. Then we can use symmetric decryption and re-encryption along the path to move data along the circuits that are established. This is the basic idea of Tor, the second generation onion routing network, which was specifically designed for low latency, anonymous internet communications like web browsing. It's been running for almost 20 years and has about 2.5 million users, and it's fairly easy to use. It's also freely available, and it's possible to use it for anonymous web browsing. There's even a version of Tor that's built in to a web browser called Tor Browser. The main software of Tor is the onion routing protocol itself, but it's important to know that when people talk about Tor, sometimes they're referring to the Tor Project, which is a nonprofit organization that participates in many different activities and also sponsors other software projects such as Uni, which we've explored in a previous lecture. Tor routes traffic through a sequence of so-called onion relay nodes. You can see here that traffic is encrypted all the way from the client to the exit relay. Every relay along this path removes a layer of encryption, hence the analogy to an onion. The exit relay removes that final layer of encryption and sends the traffic onto the destination. By virtue of onion encryption, every node along the path only gets to know about where the traffic came from and where it's going next. But unless you're an adversary who has access to both the entry and the exit, it can be very difficult to correlate traffic that's coming from a Tor client to the ultimate destination for that traffic. In onion routing, a user creates a circuit leading to their destination, and at each hop, the node unwraps a layer of encryption or a layer of the so-called onion, revealing the next destination. But only at the exit node is the final destination clear. And the exit node, of course, doesn't know which Tor client originated the traffic, so it also cannot correlate sender with receiver. Client applications connect and communicate over an established Tor circuit, and the datagrams are encrypted and re-encrypted at each link using the symmetric keys that are exchanged when the Tor circuit is established. Tor clients send traffic through all circuits that they use with a selected guard, and the relays define individual exit policies, in other words, which exit nodes they're willing to communicate with. Clients then multiplex multiple streams of traffic over a single circuit, and new circuits replace existing ones periodically to make it more difficult for an adversary to perform certain kinds of traffic analysis. In addition to multiplexing TCP connections over a single anonymous circuit, Tor has a number of other management issues to take care of, including how a client discovers the entry nodes, or so-called guard nodes, in the first place, as well as to control how new Tor routers are able to join the network. Because anybody can run a Tor relay, it's possible that the attackers themselves create a large number of Tor routers, thereby compromising the network. This is called a Sybil attack on the Tor network, and there are various ways that researchers have developed to try to detect Sybil attacks. One of the biggest threats to privacy in Tor is traffic analysis, and a well-known attack is so-called website fingerprinting. The idea here is that an adversary who may be able to observe some of the traffic, either at the entry to the Tor network, at the exit, or both, is able to observe patterns in the encrypted traffic, either sizes of encrypted packets, timing, or both, and determine who the sender is, who the receiver is, and sometimes even what the content is. For example, which web page a user is visiting. Now that might seem far-fetched, but web pages actually are fairly unique in both their sizes and the number of objects that they tend to serve. And so as a result, an adversary can often figure out who is talking to who, and even which website is being visited, sheerly based on the timing and sizes of encrypted traffic. Sometimes a user's DNS traffic may not be routed over the Tor network, or the Tor exit relay itself might use a public DNS server for its DNS lookups, thereby making the user's traffic vulnerable to fingerprinting as well. Here you can see some advice from the Tor mailing list where someone suggests to the operators of Tor exit relays not to use Google's public DNS servers. At the time, more than 40% of the Tor exit relay traffic corresponded to DNS lookups to Google's public DNS servers. It's also possible for an adversary to deploy rogue exit nodes, which could make certain types of traffic analysis attacks more possible as well. In thinking about adversaries, we could think about node-level adversaries who can compromise individual nodes or groups of nodes. potentially nodes that are hosted in the same ISP or the same cloud service. And we can also think about link-level adversaries, where an adversary might have a fixed location, but may control one or more autonomous systems or internet exchange points. In summary, Tor is a multi-hop network designed for anonymous communication that draws inspiration from mixed networks, but is designed for low latency. It has more than 2 million users from around the world, and many people use it for censorship circumvention in addition to its initial design goal of enabling anonymous communication. Many of the attacks against Tor involve traffic analysis and blocking to access of the guard nodes. And so in the design of Tor, it's very important to control who has access to those guard nodes and how clients ultimately discover them.